Hello everyone. In this video, we are going to discuss the solution of the exercise problem from USACO 2020 US Open Gold Division. So in the problem, we have n cows. They are labeled from 1 to n. N can be up to 10,000. And using some permutation of n, we have to change places of the cows. And at the end, they are going to come to their original positions. And for if different permutations of A, we have different number of the steps. And in the end, we have to make sum of all those distinct steps. For example, if we have this permutation 1, 2, 3, 4, 5, so we don't change the place of the cows, they remain in the same position, so step will be 1. But if we have this permutation, so the step will be 6. And for n equal to 5, the sum of such distinct steps is 21. And here we have this value. We have to calculate that value. It can be large one, so we get the modulus of another value here. The second number is always prime. So let's follow those steps and see how it is working, that permutation. So for n equal to 5, we have 5 cows. And at the beginning, they are in order. So those are the cows. And we have another vector with n elements. And here we have a permutation of A. This vector is A. And in the sample, we have 2, 3, 1, 5, and 4. So using the vector A, we have to change the positions of the cows in the first vector. And here, the cow in the position I goes to the position AI. The first cow goes to position 2, second one 3, third one 1, and so on. Now using this permutation, let's change the positions of the cows here. The first one goes to second position, second one third position, and the third one goes to the first position. Fourth one goes to fifth position, so 4 comes here in position 5. And the fifth one goes to the position 4, so 5 comes here. So after the first step, this is the new order of the numbers. Until we obtain the original order, we continue. So 3 goes to position 2, 1 goes to position 3, that 2 comes to position 1, and 5 goes to position 5, and 4 goes to position 4. So after step 2, we have this order. And then we continue. 2 comes in position 2, 3 is here, 1 here, 5 and 4. So after step 3, we still didn't get the original position, original ordering. We continue. 1 comes here, 2, 3, 4, and 5. Step 4. And 3 comes here in position 2. 1 goes to position 3, 2 goes to position 1. Pardon, this is 1. 5 and 4. And let's check this step 6. So 2 goes to position 2, 3 goes to position 3, because we have this permutation. So 2 goes to position 3, and 3 goes to position 1. So the third number is 1 goes to position 1. Fourth one goes to position 5, so 5 comes here, and the fifth one goes to position 4. And this is step 6. So after 6 steps, we get the original order. 1, 2, 3, 4, 5. So that for that permutation, we need 6 steps. For different permutations, we need different number of steps. And in the problem, we are asked to make sum of all those distinct steps for different permutations. So here, how can we get these 6 without simulating all the steps here? If you notice, in this permutation, we have 2 disjoint cycles. So those elements are changing their places in this group. So 1 goes to position 2, 2 to 3, 3 to 1. So this is one cycle. And also we have another cycle here. And those cycles are disjoint. And the size of the cycles are important here to calculate the value. So the size of the first cycle is 3, and second one is 2. And here the number of steps we need is 6. So if we multiply them, we get 3 times 2 is 6. But actually this 6 is not the product of those values. Actually this is a least common multiple. For example, suppose that we have those cycles 3, 3 and 2 elements. So for n equal to 8, we may have those cycles. And here, what is the number of steps we need? So it is not 3 times 3 times 2, but it is only 6, because 6 is the least common multiple of those values. Because those two cycles have the same size, so whenever one of them comes to the original ordering, the second one also must come in the original ordering. So we can eliminate one of them if we have the duplicate values as size of the cycles. So the result will be 3 times 2. And also we have, for example, 2, 4, and 2 and 4, let's say. The result will be 4. Because 2 times 2 makes 4. So when in 4 steps, this cycle comes to their original position, and this one comes second time to its original position. So actually we don't need all the sizes to calculate those values. But first let's try to find out this 21. If we can get 21 using those disjoint cycles. So for n equal to 5, let's find out the sizes of the cycles. And their least common multiple. So for 5, we may have 1 plus 1 plus 1 plus 1 plus 1. So 5 cycles, each cycle has only one element. So their least common multiple is 1, because they will not change the position. So we need only one step. Also, it can be 1, 1, 1, and 2. 3 groups with one element and one group with 2 elements. The result will be 2, because when in the second group the numbers come to their original positions, the others will come second time to their original positions, and after 2 steps we will get the original ordering. So the least common multiple of those values. And also it's possible we may have 1 plus 1 plus 3, and this time the answer will be 3. And we may have 1 plus 4, the answer will be 4. So starting with 1, those are the cycles we may have. And also we can have, in one cycle we may have 2 numbers, in the other one 3 numbers, and 2 times 3 is 6. So we need 6 steps to put them in their original order, because this one requires in 2, 4, 6. It will come to original positions, and this one comes in 3 and 6 to original position. So they are going to meet in this step 6. And starting with 2, we may not have another one. So with 3, we can have 3 and 2, we already got this one. For 4, we can have 4 and 1, we already got this one. And also we can have one group only with 5 elements, and we need 5 steps for this one. Did we forget any of them? And also we may have 1, 2, and 2, 3 groups, and their least common multiple is 2. And what else can we have here? We got 2, 3, 1, 4 we got. I think those are all the cycles we may have. And here, what is the distinct number of the steps we can get? We can get 1, 2, 3, 4, 5, 6, and 2 already we got here. And sum of those values is the answer. So 1 plus 2 plus 3 plus 4 plus 5 plus 6. So the 6 times 7 over 2 is 21. So for n equal to 5, the answer is 25, like in the sample input. But here, enumerating all the cycles, then calculating their least common multiple is a slow process. For 10,000, it will be a slow solution. So here we need to make some optimizations and calculate those groups quickly. So actually here we don't need all the groups, because once when we multiply them with 1, the result will not change. So we can eliminate the ones, and we may need 2, 3, 4, 2, 3, 5, and also 1, 2, 2 we don't need. We only 1 and 2 will be okay. And 1 and 2 we got here too. For example, let's make the calculation for n equal to 7, and we write only the sizes we really need to calculate those values. So let's make it for n equal to 7, and here sizes of cycles, and the least common multiple. So we can always have 1, because the size of each group can be 1. So 1 will be useful all the time. And also we can have 2 plus 1 plus 1 plus 1 up to 7 we can make it. So least common multiple will be 2. With 2 we can have 2 and 3, because 2 and 3 is 5. The other 2 can be another 2 or 1 plus 1. So this will be 6. And also we may have 2 and 5. Their sum is 7. So this common multiplier is 10. Starting with 2, we can have 2 to 4, but 2 and 4 is the multiple of 2, so we don't use this one. We may have 3 alone, because the others all can be 1, 1, 1, and 1. So here we have 3. With 3, we can have 3 and 4 together. Sizes of the group, so this is 12. And with 3, we may not have another. We can have 3, 3, and 2, 1, but it is the same here. And we can have 4 alone. We can have 4 and 3. We already got this one. And we can have 5 alone. So it is 5, 1, and 1. We can have 6, but 6 is 2 times 3, so we don't use this one. And also we can have 7 here. So for 5 we have 5, for 7 we have 7. And some of those values will be the answer when n equal to 7. So it is 3, 9, 19, 22, 44, 48, 38, 43, and 50. I am not sure if this is correct. We can calculate it. And here we eliminate the sizes we don't need, the redundant ones. Only we need to get those sizes to calculate the result. So if you notice the numbers here, those numbers are actually power of the primes. So those are powers of primes. This is 2 power to 0, 2 power to 1, 2 power to 1, and 3 power to 1, 2 power to 1, and 5 power to 1, and so on. So if powers of primes is not larger than n, we use those sets. And here in the problem we have to find set of the powers of primes if sum is not larger than n. And for each set we have to calculate this common multiple, and sum of those this common multiple is the answer. If you notice here, we don't repeat the same groups in the left side. So here, what I actually have here, sets of powers of primes where for each set sum is not larger than n. So in the problem we have to, using those sets, we have to calculate those values, and sum of those values is the answer. So again, if we generate all the sets and get calculate the least common multiple, is a slow process, but there is a dynamic programming for that problem, for that part of the problem. It's a well-known algorithm. So to calculate, to get those sets, and calculate the least common multiples, we use a dynamic programming here. In that DP solution, actually it's a knapsack-like dynamic programming. But first, we have to get all the primes. So we have to get a set of the primes smaller than or equal to n. So step 1, we should generate all primes smaller than n. For n equal to 7, the prime numbers are 2, 3, 5, and 7. So using this series of Aristotle's algorithm, we can generate all those primes. After that, we use a you can use a matrix in the implementation, or you can use two separate vectors. So let's use two separate vectors. So this is, let's say, our dp vector, and here dpi keeps some of the multiples for I. So at the end, some of the values here will be the result. If n equal to 0, we always get one solution, so we don't end it here. The others are 0 for now. So for each prime numbers, we have to calculate the sets. It is all the sets, they contain the power of that prime. And for that one, the contribution of that set actually into the result, we use another vector, temporary one. Let's make them the same column. 1, 2, 3, 4, 5, 6, 7. So when we calculate the sum of those values, we always multiply the power of different primes. We never multiply 2 power to 1 with 2 power to 2. Because their least common multiple is always 2 power to 2. So we don't need to calculate with the other powers of the same prime numbers. So in those groups, if you notice, all the powers of primes are distinct here. For the base is different prime numbers. So for each prime, we keep the values in the second vector. Let's call them temp. We initialize it to zeros. So for each prime, when the base is prime, we use we refresh this temp. We initialize it to zeros again. So the first prime number is 2. So when we have 2 power to 1, this is 2. And for this 2, we have to multiply it with the result of other powers, other primes. And so far, we have only 1 here. So 2 times 1 is 1. It means if I is 2, we need 2 steps. So if there is only one group with 2 elements, we need 2 steps. That means. Then here, because there is no other ones, all when we multiply them with all others, they will be 0 and will not change here. So for 2 power to 1, we update the second value in tab to 2. And then we make the same to 2 power to 2. It is 4, smaller than n. So we use the dp vector to update the values in temp. So the first one is 1. 1 times 4 is 4. And 0 plus 4 is 4. So this value becomes 4. 0 plus 4. We add it. And there are no other ones in the dp vector. So this is when we get the values from 2 power to 1 and 2 power to 2. The next one is 2 power to 3. But this is larger than n, so we don't make any calculation. After that, we add those values to the original dp vector. So 0 plus 2 is 2. And 0 plus 4 is 4. So we are done with 2. So next prime is 3. For 3, we initialize temp to zeros again. And we start with 3 power to 1. This is 3 smaller than n. And for each value which is not different than 0 in dp, we multiply it with 3. So this is 1. 1 times 3 is 3. So 0 plus 3 is 3. This value becomes 3. Then this is 0. The next value is 2. 3 times 2 is 6. And 3 plus 2 is 5. So this value becomes 6. If n equal to 5 and we have 2 cycles with the size 3 and 2, we need 6 steps. That 6 means that we have one group with 2 elements, the other one with 3 elements. So let's continue. The next value, which is different than 1, is 4, but we have to check 4 plus 3. It is 7, not larger than 7. We continue. So 3 plus 4 is 12, and 3 plus 7 is 4 is 7. So here we update 12, 0 plus 12. We multiply 3 with that value, and we add 3 with the index of this one. If the sum is not larger than 7, we update the value. Next power of 3 is 2, but this is larger than n, so we stop it here. And again, we add those values from temp to dp. So we have 3 here and 6 here. We add them back. So next prime is 5. So we make same operation for 5. Again, we initialize temp to zeros. So 5 power 1 is 5. And using the dp, we multiply the values with 5. 5 times 1 is 5. 0 plus 5 is 5. So this value becomes 5. And the next value is 2. Until 2 we continue, because 5 plus 2 is 7. The others will be larger than 7. So 2 times 5 is 10. And here we have 10. And we are done with 5, because 5 power 2 is larger than n. And we copy back those values. So this value becomes 11, and this value becomes, and here we forgot 12 in the previous step. We already got 12 here, and add 10, it becomes 22. Because we add 6, then we forgot 12 here. We are done with 5. The next value is 7 next prime, 7 power to 1. And we only get 0 here, because 1 plus 7 is 8. So 1 times 7 is 7. This value becomes 7. And we add them back to the dp vector, and this one becomes 29. We are done with all the primes, and some of those values is the result. So it will be 1 plus 2 is 3, 6, 10, 21, plus 29, so it makes 50. We got the same value. So this is how we solve that problem. Using dynamic programming, first we generate all the prime numbers up to n, and then for each value we calculate how many different steps we need until here. Because if we calculate for 3, the rest of the cycles may have on the size 1, and still we can use these steps for 8, for n. And some of them is the result. So what is it? So this is how we implement with using only 2 vectors in O and space. But you can, instead of copying each time back, you can use a matrix, and you can fill it in row manner, and in the last row some of the values will be the answer. So my implementer, I get n and m, and I use a global variable for primes. I use CF Eratosthenes algorithm, and here in the primes we get all the prime numbers. After that, this is how we calculate it in the dynamic programming. For each prime number, we use a temp, initialize it to zeros, and if power of prime is smaller than n, we make it like that. In the dp vector, we check if the value is even 0, doesn't change anything. We multiply the solution of j in dp with the power. The power is the power of the current prime number, and add it to temp. And after finishing with one power here, with one prime here, we copy them back to the dp vector. And after processing all the prime numbers, at the end, sum of the values in dp vector will be the answer. But here the answer is a big number. We have to get the modulus of m here when we make a addition here, and when we make multiplication here, and when we make another addition here. And also the type should be a long integer. At my first implement I use int, and it is not large enough. If you use long, then it will be okay. So this is how we can solve this problem.